So, uh, so let's try to review what we saw last class. The idea of torque and angular momentum. Okay, so the first thing is that the rotational kinematic formulas we can rewrite here now. You know, very similar from the linear now to the rotation motion. You know, the final angular velocity is equal to the initial plus the angular acceleration times the time. So it's very easy to rewrite those formulas. Again, if I have a particle going on a circular motion, the angular velocity, if it's going counterclockwise, the direction of the angular velocity is going up, and that's the right-hand rule. If going this way, it's going up. If it goes the other way, it's going down. Okay? So this is important to remember. Another important formula starts from this distance here, on the curvature, is equal to the angular displacement times the radius. Okay, this form also comes from here, where the linear velocity is the distance of the circumference divided by the period. And from here, 2 pi over the period is the angular velocity. So those formulas are pretty easy to come up with. You know, you don't need to memorize anything. You can always make this drawing and write them down. Even though you guys are going to have a paper with the formulas, it's good to see where they're coming from so you have a better understanding. So here, from this formula now, when there is a change in S with time, right? Change of space with time is always related to the velocity. The change and the angular displacement with time is an angular velocity, and then we have the radius. So the first time we do a rate of change, then the next rate of change comes to the acceleration. If you see this in sequence, it's very easy to understand. And this is the tangential acceleration now. Remember when we were talking about uniform circular motion, the only acceleration there was what? What was the only acceleration we had on a uniform circular motion? Where is the acceleration that causes some particle to do a circular motion? Centripetal, right? The centripetal acceleration is the acceleration that creates, you know, a circular motion. You have to have, yes.
What does the V stand for in that one?
V here?
One above it. V equals W.
V, this is the linear velocity equals the angular velocity times R. And that comes from here. Do you understand this formula here? Yeah, so if you understand this formula, now when you vary that with time, then you have this, the linear velocity, the one that goes up here, right? The velocity, the direction is changing. The speed is the same in this situation here, okay? That's what we call the uniform circular motion. Uniform because, not because the velocity is the same, but because the speed is the same, okay? The velocity is changing because the direction is changing. Only the direction is changing, not the magnitude of the velocity, okay? So when that happens, then you have this formula, and from here we rate of change with time, that becomes the linear velocity, and this becomes the angular velocity. Okay? How fast is this angle changing? Right? The same as linear velocity, how fast a certain distance is changing. That's linear velocity. Now, from here, if the velocity now is changing with time, right? That's the rate of change. The rate of change in velocity is an acceleration. And now we have not a uniform circular motion, but a non-uniform circular motion. Because what happened now, not only the direction of this tangential velocity is changing, also the magnitude of that, of the speed, is changing, okay? So now I have here the equivalent to the linear acceleration, right? The tangential acceleration, and now I have the angular acceleration. This alpha here means the angular acceleration times the radius. And this is the centripetal acceleration. That is the one that is causing this particle or this object to go in a circular motion. Okay? So it's important to review that before we move on torque. Based on what we saw last class, can anybody tell me what is torque?
Like the speed at which something is turning at an angle, like angular, like, can't think of the word, I know what it is, I'll describe it, I remember it though.
Yes.
Which is a good question. How do you derive the centripetal acceleration? The v squared over r.
Oh, this one here, we did this before, right? The centripetal acceleration, when you have this going to the center, and that goes with the angle here too, right? That angle is changing. We have a delta V when we go up to here. This is V, and this is a delta V now. The delta V is going towards the center because, you see, at the moment I move a little bit here, this thing goes this way. The delta V goes this way to the center. So there's a delta V over delta T. Right? And that goes to the direction of the center here. But the question is, what is torque in relation to the force? Yeah.
Is that the force that causes the rotation?
It's a kind of similar to the force, right? The force is causing an acceleration, right, in one direction, but here the torque is related to a rotation, right? So, so if I were to relate force with an acceleration would be with A, right, the linear acceleration, and torque is with the angular acceleration, right? When I apply a force, there is an acceleration, right? If a body or a car is moving, if there's no force, the velocity is going to be constant. But the moment I keep applying a force, this velocity is changing. And if the velocity is changing, that means there is an acceleration. Now, in order to cause a change on a uniform circular motion, right, I need to apply a torque. It's like, trying to open the door, right? And the torque, of course, the torque needs a force, right? The torque needs a force. So in order to open the door, I need to apply a force and the axis so I can rotate, right? If there is no axis, there will be no rotation. Okay, if I have this roller here, let's say this is well balanced here, and this is in equilibrium right now. So if I apply an extra force here, you see it start a rotation motion here, right? This thing keeps rotating, and if I keep applying the force, it's going to continue to rotate. Okay? So this here, let's say I have this bar, and this is the axis here. Like I have this marker, and this could be the axis. If I apply a force like this, right, then I have a torque. Now, the torque, let's say here, if I apply the same force in different locations in relation to the axis, you see that the result is going to be different. Do you see that happening? Yes.
Similar to the work, right? It's like work. Work is force multiplied by distance. like
Yes.
that.
See, but this is rotation,
yeah.
right? The work you're talking about is linear, right? The force with a linear displacement, that would be work. Here, I'm applying a force, and this thing here is just rotating. Now, my question is, if I apply the same force in different locations, is it going to be the same torque? No, right? And you can feel that when you try to open the door. If you open the door at the most distance from the axis here, this is the axis, right? It's easier to open the door here if I try to open the door here, if I apply the same force, right? So, and that is because torque is the distance times the force. So this distance, it's an important parameter here that we need to consider, okay? Another thing, another aspect that I want to show you is that when the force is not perpendicular, what do you think is going to happen? If I apply the same force in this direction and the same force in this direction, which one will have the largest torque?
Second.
The second, right? The perpendicular, right? Because here, I'm basically wasting some components on the x-axis, right? What happens if I apply a force in this direction? What happens? Is there a torque? No, right? Why? Because the sine of 0 is 0, right? So that makes the torque equal to 0. So from here, torque is a cross product between two vectors. The cross product between two vectors is a vector, right? You guys remember that, right, from the basic math that we reviewed last class. The dot product is the product of two vectors, but that is a scalar, right? For instance, work is the dot product of two vectors, the displacement and the force, but work is not a vector, all right? So those are main points that you guys need to remember. Now, another thing, the same as the cart. The cart, if I do a little push and it keeps moving, it's not going to change its speed speed unless I apply an external force to it, right? We have that in our understanding now, right? Now, what I want to expand that a little bit is that the same is true for angular velocity. In order the angular velocity to change, we need to apply an external torque. Yeah. You know, I know, you can say force, but if you apply a force that is in this direction, you're still applying a force and it's not causing any rotation. Has to be connected with the rotation idea. The rotation idea is a torque because it's a distance and the force. Remember when I said that here we are wasting the component on the x-axis of this force is being wasted because it's not causing any torque. To cause torque, you need to have a force that is on the y-axis here, okay? So, again, angular velocity to change, we need an external torque similar to what we had in the linear motion. We had to have an external force. Is that sinking in? It takes time, but that's the language that I'd like you guys to become familiar with. So it is also important to understand the meaning of the center of mass. What is your understanding about the center of mass?
Both sides of like a system have to be equal to each other, like we have up here.
Yeah, like here, right? So if I change the weight now, this is 100 grams, and if I change the weight now to, no, this is 1,000 grams. If I change the weight now to 500, so you see that the equilibrium, the balance is broken. What? Uh-oh. Where is it? Where is here? Huh? The balance was broken. So what should I do in order to balance this out?
Move the center of mass.
Move the center of mass, right? Let's see if I can fix this. Okay. Okay. So should I move closer to the middle point here? And let's see if this is going to work. So I keep moving. Good. Looks pretty much now. Now, if the weight here is twice as much as here, in order for this to be in equilibrium, this distance has to be twice as much as that one, because this is the product, right? It's the product of this distance times the weight, this distance times the weight, and they need to be going in different directions here and balancing out. So this one is going in this direction, so the torque is pointing to that direction towards you. And here, this one is going in this direction, so the torque is pointing on this direction. It's like two forces. Remember when we had the normal force? If I put a weight here on the table like that, right? It's not going anywhere because, the forces are canceled out. The sum of forces here is 0. Now, on a circular, you have to remember now is the sum of torque is 0, right? Is that, you see the torque has different directions, the vectors. That's why we vector notation and understanding we have created this idea of vector, so we can explain things. That's the importance of vectors, okay? Yes,
Would you mind reading the definition you wrote?
reading here?
Yeah.
Yeah, I'm going to that.
Oh, sorry.
I didn't go, yeah, that's okay, yeah. You know, I wanted to talk about what is center of mass. Like for instance, how can I find the center of mass of this here? Is there any way you think I could find the center of mass? Where is the center of mass?
Center of the card,
Is what?
like the center of the
The
card.
center of the card, right? So let's do some testing here. Do you guys, let's do some testing here. I'm gonna try to apply a force. If I apply a force that is off the center of mass, what do you think is gonna happen?
Card will move that way.
The car is going to rotate, right? You see that? You see that? I produced some rotation here. Now, what do you think is going to happen if I apply the force close to the center of mass? What do you think is going to happen? It's going to be circular motion? Huh? Can you-
It'll be straight.
It's straight, right? So if I apply right here, now you see it becomes linear motion, right? It's like I have a point. This object is like a point right there, and I apply a force, so that's going to be a linear motion. So what is the center of mass? Is this unique point where we have the masses well distributed here, right? The distribution of mass, the sum of them is equal to 0, okay? So, so how we can use that? So if I apply a force in the direction of the center of mass, it's going to be linear acceleration only. We will not have angular, okay? We can have angular and linear acceleration, right? So we can have both. But if I apply the force only to the center of mass, that's going to be just linear. In order to cause rotation, I need to be off the center of mass. Okay? All right. So, so what is the condition of equilibrium? The sum of the forces is equal to 0. The sum of the torques is equal to 0, right? That's the condition of equilibrium. So if I have this bar here, the center of the bar is here, and the bar has a weight of m2, and I put an m1 here. What do you think is the value, relative value between m1 and m3? If I were to ask you, I'm saying the center of mass is right here. What would you say? What can you say in terms of the relative mass between M1 and M3?
M3 will be greater than M1.
M3 is greater than M1? What is it?
And one is heavy because the center is the same.
M1 is heavy, right? Remember, the torque is this distance times M1, right? And it's going to be this distance times M1. So this distance is larger than this one here, and if they're in equilibrium, it's exactly like this.
Oh, I didn't know you said they were in equilibrium. I thought you just meant like what would happen if we had like a center of mass at a different point.
Right. Yeah, because it's written here condition of.
No, I understand it. I
Yeah.
thought the question was.
Yeah, okay. So is this clear, right? So if this is in equilibrium, and this is a typical problem, okay, that we're going to have that next exam, okay? So if I give you values of masses here, and you're going to be able to calculate, you know. So how do I calculate the torque here, the equilibrium torque? The torque on this side, going this way has to be equal to the torque from this side. And here we have two components, right? Because we have to consider the weight of the ruler also. This is a ruler, right? The ruler has its weight, okay? So the distance between this point and this point times M1 has to be equal to the distance from this point to this point times M2 plus the distance times M3. And from here, we can solve for x, finding this position here, okay? So if I give you mass 1, mass 2, and mass 3, and the total distance, you should be able to calculate the position of the center of mass. Is this something you guys feel you can do it? Yes.
When you go M2 times the distance,
Mhm.
is that distance the same for M2 as it is for M3, or is it just from that point to?
No, it's from this point to here.
Okay.
The distance is not the same. This is x1, this is x3. Okay, it's a different location, right? It's the same like the door. If I apply the force at the most extreme part of the door, right? And if I go to the middle of the door, there are different positions, right? So the force locked in to a position. All right? So what was written here is that the center of mass is actually a very unique point relative to the mass distribution, right? That's what's written here. So the sum of them equal to 0. Now, I have here a problem. This problem here, we have a bar with an axis, and I have a force going in this direction equals to 3 newtons. I have a second force here on the extreme equals to 1 newton, and I have one going in this direction equals to 1 newton, and I'm asking you to calculate the force of F. So this is in equilibrium. So can you calculate that now? Can you try to calculate that?